This lesson is looking at applying some of the skills that we already know to work with real-life problems. We're going to look at three different formats of log scale used in current day. The first one is looking at pH scale. We'll follow that up by looking at the decibel scale, and we'll also look at magnitude, which in terms of the Richter scale. All three of those are based on the log scale, and we'll try and explain why. And so let's take a look at the first example, pH scale. pH is a way of representing some very small ions, hydronium ions. And the reason that we introduced the log scale is for pH. When we talk about pH, pH runs from a scale of 1 to 14, where standard sort of drinking water would be approximately 7. Acidic items like lemon juice and tomatoes would fall between 1 and 7, and alkaline things like baking soda would fall on a much higher on the pH scale. Now, this range of 1 to 14, we can compare things very quickly. If we are talking about the hydronium ions, which is actually what we're measuring, we're talking in very, very small numbers. In fact, 1 times 10 to the negative 14, which is very hard to relate to. So this pH scale really does come into play, but it is based on a log scale. And so we're going to use this formula to help us determine what the pH of certain elements are. So I'm just going to jump back really quickly and finish up this first note. It talks about, in order for us to compare this vast range of either very, very small numbers or very large numbers, we can use logarithms. And logarithm scales are often used in situations where we're dealing with large or small numbers of powers of 10. And so let's move right into this example talking about tomato juice. Now, tomato juice, if we were to get a drop of tomato juice in our eye, it would burn. And is that because it's very acidic or because it's alkaline? If it's neutral, much like a droplet of water, it may make our eye water, but it's not going to have a lot of pain or lasting pain. So working with tomato juice, we have a prediction that the pH might be some number between 1 and 7. Let's use the pH formula. pH is equal to the negative log of the hydronium ion concentration. Don't get confused with the little plus sign. It doesn't mean exponent. It just stands for hydronium ions. The square brackets are guiding us that we're talking about concentration. So this question, we are just going to substitute in decimal 0.0001 as the hydronium ion concentration. When we plug this into the calculator, we get a positive value of pH. And so that pH might fall somewhere in the middle between 1 and 7. Orange juice has a pH of approximately 3. What is the concentration of hydronium ions? So once again, we're going to use the formula, but this time we're going to plug in the pH and solve for the hydronium ions. So 3 will go in where pH is, because that's what we know it is, minus or negative log of hydronium ions. Now for a moment, think of this question as one that you've done many times before, and replace hydronium ions with x. Well, if this was the question and you couldn't get any farther, then one strategy is to change it to its exponential. There is a 10 down here for common log, so this would be 10 to the power 3 is equal to x. The only thing we have to be concerned about is the negative, so I'd suggest dividing the negative out first, and that will make this a negative here. So we'll show this in this example. So once again, the first step is to divide or multiply both sides by negative 1. So we end up with negative 3 log of the hydronium ion concentration. This is a common log, so now we're going to change it to its exponential and solve for H positive or hydronium ions. 10 to the negative 3 is 0.001. And we can answer, therefore, the hydronium ion concentration is 0.001, and again the units are important here, and in the question it does tell us, if we go up a little farther, it is in moles per liter. So moles per liter. The next question is involving the decibel scale. Once again, a different formula. We have to identify what each of these values look at. So a lot of these questions are relating different sound levels and talking about their intensity. So this is what the formula reads. B2 and B1 are the sound levels in decibels. So if we're talking about how loud a jet engine is compared to how loud a car or a motorcycle is, those would be given in decibels. And we'll look at a decibel scale in a second. 10 multiplied by the log of the intensity. So this is the ratio of the intensity. Now, I want you to simplify this and really just think of this question or this formula as 10 log intensity, even though it is I2 over I1. There will be a few scenarios where you have to use I2 over 1, but if you're asked to solve the relative intensity, you're really just solving for I. So let's take a look at an example here, and then we'll talk about the units as well. How many times as intense as a whisper is the sound of a normal conversation? Well, in these questions, you will be given the actual decibels, or you'll be given a scale. So in this particular question, they talked about a normal whisper, or sorry, normal conversation to a whisper. So we're dealing with a 60 decibels versus a 30. So there is B2, and there is B1. And a little hint, make the louder of the two B2. It just makes for a little bit easier math. So if we go back to this question now, I'm going to substitute 60 in for B2 minus the intensity of the whisper, which was 30, and begin to solve for the intensity. So how many more times is intense? So we had 10 log of, I'm just going to put I. $60 minus 30 is 30. Divide both sides by 10, and 3 is equal to the log of I. Once again, to solve for intensity, we need to rewrite this as its exponential, and therefore we see that a normal conversation is 1,000 times as intense as a whisper. Moving along, and sometimes they actually ask us to find one of the sound levels. So I'm going to rewrite the equation. B2 subtract B1 is equal to 10 log of I2 over I1. And notice that the ratios correspond. If B2 is first, I2 needs to be first here. So in this question, they tell us the sound level in normal city traffic is 85 decibels. The sound level riding a snowmobile is 32 times as intense. So if we use kind of common sense, it sounds like the snowmobile would be louder than normal city traffic. So we're expecting the larger decibels to be B2. So I'm going to leave B2 and substitute in 85. And I know that the louder one is 32 times as intense. I just start equation solving. Move the 85 to the other side, and I have 10 times the log of 32 plus 85. So if I type that in the calculator, I end up with a decibel level of just about 101. So 100 decimal 0.05. So we're going to round that off to approximately 100 decibels is the sound level of a snowmobile. Great. Let's look at the last example, which is talking about earthquakes. This is probably the simplest of the three formulas. I will tell you at this point that all three formulas will be given to you. You do not have to memorize these. These will be provided for you on the final exam. These are probably one of the few that will be provided for you. So this question is set up where M is talking about the magnitude in terms of a Richter scale. And to get a feel of Richter scale, a magnitude of approximately 8 is a devastating, huge impact on both land and area around. So some of the more recent larger earthquakes in Haiti and different parts of South America registering around 8. If they're located near a population or a city, they can cause incredible structural and a lot of damage. Whereas an earthquake around, say, 2 probably are occurring quite often. And we might notice a little shake here and there, but if you're living in southern Ontario last June, the earthquake that happened in June last year registered about a 5, and it was located in a fault in Quebec. We did feel it in southern Ontario, so that gives you an idea of the distance. It was probably about 100 or 400 kilometers from where it occurred, and we still felt it. It was very minor, but it gives you an idea of how intense these are. So the first question is, how many times as intense as a standard earthquake? Now, standard earthquake is really important because this little I naught, we call it, down below here, basically has a value of 1. And so intensity-wise, a standard earthquake has an intensity of approximately 1. That's what this is saying right here. So really what you're trying to do is, in a lot of cases, is you're trying to solve for the I above. So kind of similar to the questions we did before. So this time they tell us that the magnitude is in fact 4 on the Richter scale, and they want to find out how intense is the earthquake compared to a standard earthquake. And so what we're doing again is we're solving for I. We're into that kind of spot where we need to change it back to its exponent form. So 10 to the power 2 decimal 4 is equal to the intensity. And once again, plugging that into the calculator, 10 to the power 2 decimal 4 gives us an answer of approximately 251 times as intense as a standard level earthquake, which registers about a 1 on intensity level. The second question is talking about what is the magnitude of an earthquake 1,000 times as intense. So a 2.4 is 251 times. 1,000 times is going to be quite a bit higher. So this time we're trying to find the magnitude, and we're working with an intensity that's 1,000 times as intense. So this is going to be a question where you just simply plug in log of 1,000, and we can find this answer without the aid of a calculator because we know that 1,000 is 10 cubed. And using power law, bringing 3 in front, we end up with an answer of 3. So 1,000 times as intense only went up to a magnitude of 3 from 251 times as, approximately 2.5. So you can imagine how intense a magnitude of 8 would be and the value that it would be. So these are some of the concepts that look at pH scale, decibel level, and then finally magnitude, or what we call the Richter scale. So it is important that we use these values to help us determine how logs are used in the real world.